Yep, perfect.
All right, all right. So, as I said, this is a work I I did in my first 2 years at UCSF. Um, it's called and we published it not recently, last year actually, um, at Radiology AI, which is a journal in radiology and artificial intelligence applied to radiology in the radiology field. It's a nice journal in this area. Um, the work is entitled Automatic Deep Learning Assisted Detection and Severity Staging of Abnormalities in the Knee Joint. And I did this work while in UCSF. This is the group that I work with. Lots of these guys already left. They were like PhD students and they PhDs and postdocs, and they left, but some are still here. So this is the full paper at Radiology AI, and this work was funded by NIH and NEMS as well, but it was mainly funded by GE Healthcare. So Edgar, when I left GE, I moved to US, but I'm still working for GE in a way. Okay, so this is the team more directly involved in this project. Everything data science related it was basically me, but I also worked with Io Clement and Nikan Namiri. Nikan was an intern 2 years ago in our lab, and he helped me train the models to detect ACL abnormalities. We are going to talk about the models. Sharmila Majander is my PI, is my boss, and my co-PI is Valentina Bedoya. They are both professors in radiology and biomedical imaging department at UCSF. And I also worked with these four names here. They are radiologists. They basically provide me with labels to train the models that we are going to discuss today. So let me give you first a little bit of context on what the problem is and what we are trying to solve. So this is an MRI image of the knee. It's one sagittal slice of the knee. Here you can see the patella, and this lighter structure here is the cartilage of the patella. So the dark thing here is the bone of the patella bone, and here is the cartilage. So here the dark image here, the dark part here is the femur, is the bone, and this light, this brighter structure here is the cartilage of the bone. And finally,
sorry.
Yeah, go ahead.
We can see your mouse.
You can't see the mouse.
No.
Oh, okay. Let me do this. Okay. Can you see this now?
Yes.
Yeah.
Yeah. Okay. So this that I marked is the patella. Can you see the mouse now?
Yes.
Okay, great. This here is the femur, and this here is the tip of the tibia in your knee. And this structure here is the cartilage of the patella, and this here is the cartilage of the femur, and we have a little bit of cartilage of the tibia over here. Okay, so the problem with the knee is that we use the knee a lot, and the knee was supposed to last I don't know 60, 70 years, and with time we tend to see the degeneration of some of these important structures that allow us to move And some of the important structures that we have are the bones, the 3 bones that I mentioned here, and the cartilages that are attached to it, and they are part of this joint. And the cartilage is there to actually protect the bone. And between the cartilage, we have over here and over here, we have the meniscus, which is another structure that helps with impact absorption and don't protect the bone from impact and from abrasion as well, right? So, and when the structures start cartilage and meniscus, they start to degenerate. That's because of knee osteoarthritis. Osteoarthritis is, as you can see here, a major impact in the health related and quality of life of Americans. Here's a statistic in Brazil, according to Sociedade Brasileira de Reumatologia, almost 8% of the work-related time off is because of knee or osteoarthritis, and it's 10% of the time off and auxílio doença. I don't know how to say that in English. And in order to assess the extent of this disease in the knee, researchers have developed what they call a scoring system, quantitative or semi-quantitative scoring systems. Some of the 2 most used are worms and mokes. They are not very used in clinically, but they are used a lot in research settings. But we are going to use in particular the worms grading. So basically, they gave lesions or ACL lesions, ligaments and meniscus and so on and so forth. So we are going to use here the worms gradings. So basically, I had a number of radiologists grading several, like 1,500 images, MRI images, and giving me their scores for all these structures, all the cartilages and the meniscus in the knee. And then I use this scoring as labels to train my model. So that's basically it. The thing is that the grading this thing, this 1,500 images that I used to train my models, they were graded over like 10 years of radiology research. These gradings are very time consuming. The accuracy depends on the clinicians or whoever is grading. It depends a lot on their expertise, and they are very susceptible to inter-rater variability, meaning two radiologists are
Bruno,
lots of the time they are not going to agree. Yeah.
One question. Are you showing now on the slide called lesion and OA related knee abnormalities?
Yes. Yes. I am here. I am finishing this slide. Yes.
Okay. So you refer now to the accuracy that it's shown in the 36% for 60 years old, for example, or what about the accuracy you are talking about now?
No. Okay. So this is just data on how much the knee osteoarthritis impacts the life of people all over the world. This is a very serious disease, and so this is just to motivate the work, right? What I'm talking about now is the fact that when 2 radiologists look at the same image, they might grade them differently. One radiologist might think that it's a serious lesion, the other might think that it's a mild lesion. And some radiology might not see a lesion at all, depending on the way they look at the image, depending on their expertise and so on and so forth. So the main point here is that it's very susceptible to inter-rater variability. Okay? And one of the goals of this project is to develop, since it's very time-consuming, and you need experienced radiologists to grade and to analyze these images. So to have an automatic system to do that, and an automatic system that can aid in the grading of these images, might also reduce the interpersonal variability when reading the MRI. So this is also one of the of the goals of the project. So a little bit of context here in terms of deep learning applied to medical imaging. As you may know, I don't know if you guys don't work on a medical field, but if you guys do work with computer vision, might appreciate here this. Deep learning models have been applied in the past few years in many different areas, including like cardiology. Here we have a segmentation of, in this paper, we have segmentation of cavities of the heart in echocardiograms, the detection of pneumonia in chest X-rays, also detection of anomalies and segmentation of brain, kidney, prostate, and also spine. In my group, they work a lot with brain MRIs and also spine MRIs, not only with segmentation, but also anomaly detection, lesion detection, and etc. And also, here you can see an example of the MRI and also detection of lesions in the MRI. But in this work that I'm going to present to you today is more than simply detecting lesions, saying that, oh, it's a normal or abnormal. The goal here is to give staging of the severity. Not only say, oh, there's a lesion or there's no lesion, or it's to say, if there is a lesion, what's the extent of this lesion? Is it a mild lesion or it's a severe lesion? So, and this is very important in the clinical setting, to be able to detect that and stage and assess the level of severity of the lesions if they are present. So we would like to, in this work, to test the hypothesis that artificial intelligence techniques can aid in identifying and assessing lesion severities in the knee joint. And we look at all the structures here. We look at cartilage, we look at bone, we look at meniscus, and also the ligament, the anterior cruciate ligament. And our final goal is try to improve the overall inter-reader agreement. So in the end, we want to show that our model can aid the radiologists in grading the images and improve the agreement between different radiologists when they use the aid of the model that we developed. In order to do this work, I used a little over 1,400 images from almost 900 different patients. This data was collected over like a decade in the UCSF clinics. Here's some demographics data, like age and BMI. A little over half of the patients were women. A little bit on the the acquisition of the images that I'm not gonna talk a little bit. I'm not gonna talk much here about this. And so this is the data that I use to train, validate, and test my models on. We had also another data set with 50 MRIs, 50 MRI studies that we used it to run further evaluations on, especially on the interreader agreement. All these images, something that is important, all these images are 52 by 52, 512 by 512 pixels in plane, but they are 3D MRIs, so they have several slices. The number of slices range from 100 to 190 slices. I'm going to talk a little bit about that in the future. So here is the table. Not going to talk too much about this table. I don't know if Edgar gave you guys the paper. If you guys are interested, this data is in the paper as well. Basically, here I give you all the structures that we are interested in: the cartilage, bone, meniscus, and also ACL. And the three classes that we are interested in, which is no lesion, partial thickness lesion or mild lesion, and the full thickness lesion would be a severe lesion. So we have three classes for each region of interest. Three classes for cartilage, three classes for bone, three classes for meniscus, and on ACL we have three classes here plus a fourth class if the meniscus was reconstructed, because sometimes the meniscus is ruptured, and then they go through surgery to graft back the meniscus, to reconstruct the ligament. So on the ligament we have a fourth class, which is the reconstruction. So no lesion, partial tear, which is a mild lesion, a full tear, which is a severe lesion, and reconstructed is the fourth class. And we do this assessment for different parts of the knee. We have the lateral and medial, femur, lateral medial tibia, trochlea, and patella. We do this assessment for all the three bones and for cartilage as well. Okay, so the whole system looks like this. I think now we might be getting to the part where you guys might be interested in. So the whole system works like this. So we have the 3D MRI. I input the 3D MRI over a VNET architecture. A VNET is a deep learning architecture used to segment 3D images. We used a UNet in the past. I have a comparison here, but we'll get to this point in a few minutes. So let me give you an overview of the whole system first. So we input the 3D MRI on a VNet to segment the structures in 5 classes. So we have the cartilage of the patella, the cartilage of the trochlea, the cartilage of the femur, and the cartilage of the tibia and the meniscus. So 5 classes. I'm sorry, no, it's patella, femur, tibia, meniscus, and background. So 5 classes. What we are interested in, we are not interested only in femur cartilage. We are interested in lateral femur, medial femur, and trochlea. So we want to separate these 3 structures. We don't want to simply say, oh, meniscus, or where is the meniscus? So we want to know where is the anterior lateral meniscus, where is the posterior medial meniscus. So we have 4 meniscus horns and we would like to segment them differently. We'd like to know where the meniscus is actually located, and if it's the posterior, medial, or the anterior lateral, and so on and so forth. So we used we trained a second VNET architecture to do this more fine-grained segmentation. So we used the original inputs of the 3D MRI and the 5-class segmentation as a second channel, and the output is we trained with 11 labels, which is cartilage, patella, medial and lateral tibia, medial and lateral femur, trochlea, and the 4 meniscus horn. So it's and background. So 11 classes total. But Bruno, why do you need to the segmentations? I need the segmentation so I can locate the different structures. So I locate the structures and I crop a bounding box around this. I use the segmentations to locate the structures I'm interested in. So I used the location of the segmentation to find a bounding box and crop a bounding box around the structures that I want. Why is that? Because training a classification model with the whole volume, it's too much for the. I don't have GPU memory to train models on this amount of data, and also if I use the whole volume, I'm gonna suffer a lot with overfitting because it's too much. Too much data, and the models would overfit a lot. So, yes.
Why did you use a segmentation instead of object detection? Because you want to localize, right? Only localize, not to.
Yeah. Or why did I use a segmentation instead of
object detection, for example?
Yeah. So part of the project as well. I told you that GE was funding the project, and the segmentation is also very useful to measure thickness and volume of the cartilage. So one of the we were also interested in using the segmentations to quantify biomarkers other than we don't use the segmentation only to localize the structures. We use the segmentations also to quantify biomarkers of osteoarthritis as well, like cartilage thickness and volume. And GE was very interested in using the segmentations in their product. So the segmentation is also a product of the project. So that's it.
Okay, I got it.
Yeah. So, but in here we use the segmentations to localize the structures, crop bounding boxes, and use these subvolumes, these smaller volumes, to actually train our classification problems, our classification networks. We tackled the classification problem in hierarchically. We first trained the multi-class deep learning. Yeah, go ahead.
Yeah, I have a question. You mentioned now to my colleague that you use segmentation because you have other tasks, but have you tried probably to generate two outputs from this architecture in order to get like two types of outputs, for example, segmentation and detection, or if you want to try with instant segmentation or kind of at the end? Have you tried that, or have you thought about it?
We did not try that. So basically, you're saying one single architecture to segment and classify.
Yes, exactly. Okay. Classify or detect, well, it depends.
Right, yeah. So we did not try that. What we tried was a multi-class approach to the classification, and a hierarchical binary approaches as well. We got better results using the hierarchical because maybe it's two simpler problems rather than one more complex problem. But interesting, your question is interesting because in our group we have, I have a colleague working on MRI reconstruction, fast MRI reconstruction. Edgar, you might remember that we worked in a similar problem when we were at GE, where we had so the MRI. So the problem was to do a fast reconstruction of the MRI. The MRI is takes a lot of time to acquire the image. So because you have to go over a big spectrum of signal frequencies. So when for fast MRI reconstruction, they only read only a fewer frequencies of the spectrum. If you use less frequencies to reconstruct the image, you have a very noisy image. But they are using deep learning to fill the gaps of this reconstruction and reconstruct the image using deep learning architectures to reconstruct the image and reduce the noise and have an image with the same quality as the full sampled spectrum. Why am I talking about fast reconstruction? Because a colleague of mine, he was working on a project where he used an autoencoder to reconstruct the image, and one output of this network would be the image, the image reconstruction, and the other output would be the segmented structures as you see here. So he used a dual output network. I think he used an autoencoder. I can get his paper and refer to you guys if you are interested in that. It's a very interesting work that he did. But in our work, we use this two-step approach for segmenting the structures, and this two-step approach for classifying each one of the structures that we wanted to evaluate. First, we tried to use a UNET, and the UNET was good for what we wanted in terms of classification. But as I told you, our sponsor wanted a more precise segmentation because they wanted to use for measurement and not only for localization. Then we started studying the application of the VNET architecture to our segmentation problem, and we found that as the VNET is, so the UNET is was used to segment the structures in 2D per slice, but the VNET architecture is a 3D architecture. So we took advantage of the spatial correlation between the slices, and then it reflects on a more accurate segmentation, as you can see here. So this is the same. This is for the same knee, and you see the quality of the segmentations is very, very different, right? You might ask, so Bruno, why you train 2 VNETs and not only one VNET for 11 classes? Basically, the reason is because when we try to run to train the VNET to segment 11 classes right away, we had a lot of problems with the laterality. The network would have a lot of trouble distinguishing lateral from medial, especially because we do flipping as an augmentation technique, because we wanted to be agnostic to laterality. So we were having a lot of trouble, especially with the laterality. On the lateral femur cartilage, for example, the network would put a lot of pixels. It would say that it's a lateral, and lots of pixels it would say it is a medial. So it would not, the quality was not great. The distinguishing of the classes was not great. And we experiment with combinations of these, and we found out that if we segment first and then use another architecture just to relabel what was already segmented, then we would have a more accurate classification. So in a nutshell, the first architecture here is actually the one that actually does the segmentation. The second architecture only reassigns the labels. It changes very little, almost nothing, the values of the pixels. It maintains the segmentation of the first classes. It only reassigns the labels, like it's not the 4 meniscus anymore. It's lateral posterior meniscus, medial anterior meniscus, and lateral femur, medial femur, and so on and so forth. Any questions on this part?
Oh,
and yeah, go ahead.
No, you can go first, Leo. No problem.
okay.
Okay.
Yeah. I was about to ask that, but I was about to ask why you use two nets, but you said that it's for a kind of fine tuning, right? The second.
Exactly. Yeah.
But
so basically, the second step only reassigns the labels. It doesn't do much of segmentation itself.
Nice.
Go ahead.
Another question here. Why do you use so actually you are using segmentation for classify the in the previous slide? Can you go back? For example, in that part in pre-processing, so you are using the segmentation for classify cartilage, BMEL, meniscus, ACL, right?
Yes.
So do you? I'm curious about the accuracy of that classification. I mean,
this here, the classification here.
For example, you are using the segmentation for classify which region of interest is, right? For example, the segmentation tells you, okay, that part is the region is cartilagus. So you go to the cartilagus neural network, right? It's like a kind of if else, right?
Yeah. So I use the segmentations to locate and crop a smaller volume around the femur, for example, or the patella, and then I use this smaller volume to train the classification model. First, I train a first step that is I train as normal or abnormal. And when they are abnormal, I train a second classifier that tells me it's a severe abnormality or a mild abnormality.
Yeah, but
so I train the classification 2 steps. Yeah, what's the question?
Yeah, one step before. For example, in the part of pre-processing, in the letter C.
Yeah.
For example, if you segment one area of interest like cartilage, but the ground truth was meniscus. So I'm curious about accuracy, for example, but you can have so you have like 3 modules there, right? The segmentation, then the part of classification in the pre-processing, and
Yeah.
and the neural network for abnormal, normal, full thickness. So you
Yes.
have the like you have a lot of if you have one error in the first part, you're getting
It's
more error in the
cascade. Yeah.
last. In cascade,
That's
yeah,
very
exactly.
true.
That's a
That's
problem
very
of
true.
using. I think that's a problem of using many neural networks.
That's very true. If you made a mistake here, you screw up
exactly.
everything that goes. And this is actually something that we are trying to fix now. We are trying to develop networks that do these kind of assessment without needing to do this localization. Because this localization is prone to error. For example, here, when we are using the UNet, I can find the bounding box here just fine. But if one pixel here in the patella, the model says, oh, this is a femur, then the bounding box would be something like this.
Yeah.
Right. And then on the preprocessing part, I would do like resizing and it would screw up the whole resolution of the image, and things would not work. That's a very serious problem. So I do some cleaning, some post-processing on the segmentation, and for example, I get the biggest connected component here, and if there is a pixel here, a pixel here, a pixel there, I just delete it. I just account for the biggest connected component. I clean everything else, and then I do the cropping. That improved a lot the accuracy of my bounding box, actually.
But that region, that rectangle, you are drawing manually, right?
Yeah.
So
yeah.
I think
Yeah.
I think that was the part of the question of Oscar. The Edgar. You can use instant segmentation to do both tasks: the segmentation and the location, detection. So I think instead of drawing, instead of the idea is to avoid post-processing, right? So I think the instant segmentation can help you to do that.
True, that's true. But the semantic segmentation was also needed for the semantic segmentation itself was something that we were interested in. So it was a byproduct of the project. So that's why we focus on this kind of segmentation, and we use it since we have and we do have a very good model for the segmentation. The segmentations using this model are the quality is very good, actually. We can do better than like high 70s and low 80s dice scores. That's what we get on these evaluations. We evaluated on external data sets, and the best we can do is like 80 something dice. Even if you ask two radiologists to manually segment the structures, manually do this, their manual segmentations are not going to be better than 0.8 dice score. Even the radiologists themselves, they are going to disagree with the extent of the cartilage. It's at some point it's a little subjective. The guy don't know if that right signal is cartilage or is fluid in the knee, and he has to make a decision, and different people are going to make different decisions. So that's why we believe that this is a very a good model, and we use this for not only for segmentation but also for measuring the biomarkers for OI. This is a video. So this is I don't know if I did I answer the questions. You guys have more questions?
No, it's
good. Okay.
Edgar
All
has
right.
a question,
Yeah,
right?
yeah, I have a question. Can you go to the slide with the two VNETs that are connected? Yeah, exactly. The previous one. No, the previous slide. In the figure that you have the two VNETs connected, my question is related to the training process. Have you trained both VNETs in parallel, or have you trained first one VNET and later the other one?
No, separately. I trained 5 classes, and I use the results of the 5 classes as a second channel to train the second VNET. So the first VNET is single channel, image in, segmentation out, and the second VNET is two channels, one for the image and one for the segmentation, and it gives me the 11 class, the fine-grained segmentation in the output.
Okay, but do you think that this is the main reason, because this is working separately, is related to the number of parameters that are in each neural network that probably generate more troubles because the number of quantity of parameters probably?
The model is
related.
I think that when we try to train the 11 class segmentation right away, it was overfitting quite a bit. I think it was too big of a model and too many classes to for the network to train. So the results were not very good in terms of, especially as I said, in terms of the laterality. It would mistake a lot pixels in the lateral side and the medial side, and that was a big problem for us. And with this approach, the second network only has to say, oh, this is the medial and this is the lateral. It doesn't need to assign the pixel. What's class 1, 2, 3, 4, or class 11. So I think it's an easier problem. We made it an easier problem for the second network.
Okay, I got it. Thanks.
Here's just to illustrate. So this is an external data set. This image was part of around like 15 images that were collected in Clínica Centro in Spain as a collaboration for this project. And they manually segmented all these 15 MRIs so that we could evaluate the quality of our segmentation. I'm not going to present results. I can show you results on the quality of the assessment of the segmentation, but it's not in this presentation. I would have to go. If you guys are interested, I can show, but this is just a video to show what we want here. So on the left-hand side, you have the manual segmentation from the clinicians, from the radiologists in the clinic where the MRI was acquired, and on the right-hand side you have my automatic the segmentation that was done by the model. Okay, so you can see some differences here. So here, for example, the guy on this slide, the guy segmented everything, including the meniscus here. And in this slide, the model failed to detect the meniscus. Over here, some of the pixels here of the cartilage were not segmented, and so on and so forth. But this is a matter of fine tuning. I'm working on the continuous learning of this model to improve the segmentation and give do the fine tuning of these details here and in the coverage as well. So we missed it completely here, the meniscus in this slice. It takes a few slices for the meniscus to show up here. Another difference, so for example, here, the model detects the meniscus, and here the physician thought that this wasn't meniscus yet. But if you give to another physician, it might think that, okay, this is meniscus. So it's very subjective at this point, especially when the structure starts and when it ends. So especially in the borders, on the peripheral slices, it's a more difficult problem. It's tricky. Okay, so. All right. Okay, so we talked about segmentation. So we talked about the segmentation part. Now we're going to talk about this part here. We are going to talk about this part here, which is the classifiers themselves. So this is my classifier. I use the same architecture for all the models that all the detections that I showed in that previous slide with the whole system. So all these boxes here, they are all the same architecture, which is this one. Okay. So there's a first convolutional layer with 24 kernels, and the second convolutional layer with 24 kernels. I have a skip connection here. I concatenate the output of the first layer and the second layer to give to use as input for the posterior convolutional layers. Why do you have this concatenation? Because this concatenation gives me it gives now an output with different levels of different scales of the features of the image, and that helped the training. So I experimented with the concatenation, with and without the concatenation. The concatenation actually helps, and I think it is because of the posterior convolutional layers. They have different scales of the features, and I think that helps the training. So after the concatenation, I pull. I use the 3D pull, and then I have three boxes of three subsequent convolutional and pooling layers. In the end, I flatten the volumes, and I use the two fully connected layers to give an output of a binary output of lesion or lesion. So you guys have any questions so far?
Why didn't you try? Sorry, why didn't you try more skip connections?
Why I didn't try more skip connections? I did. They don't help. They increase the size of the model, and yeah, they increase the size. If I put more skip connections, they would increase the size of my model, and I had to fight over fitting a lot, and to train these models. I did a lot of data augmentation. Used a lot of regularization, and I had to maintain my model as smaller as I could, because as I said, I had to fight over fitting quite a bit. I did try more skip connections, but they didn't help. This configuration is this configuration gave me the best outcomes.
Okay.
Of everything that I tried, and I tried a lot of things. I did I did a lot of research on the parameters, and I experimented with different versions of these architectures as well.
Actually, as I see, all the structure is the same, but you only did you only change the only different part is at the beginning, right? Doing a skip connection and concatenation. So if you do a skip connection or concatenation in the last part or in the middle, you're going to get worse results, right? That's interesting.
Yeah, that didn't help with the more skip connections on further skip connections that they did not help with the classification.
Edgar?
Yes, my question also is related to the architecture. Have you seen the new modules like squeeze and excitation blocks or efficient nets? Because probably the new tools can be added in the middle. Skip connections usually come from DenseNet, and this is one of the reasons it works, like for example, in vanishing gradient and normal problems in deep learning. But probably there are the new blocks can give you more improvements. Have you tried with some of them?
I did not know. Can you point me to the papers? I would like to take a look at this. So this work is almost 2 years old now. So I'm sure there's stuff that we can do to improve these models already.
Yeah. Also, these new strategies come only in the 2D images, right? They are not available on 3D, but probably you can try to include them in the 3D convolutions.
Right.
I think.
Well, maybe, yeah. Well, I would like to understand the concept and maybe try to do. Maybe it's possible to convert it and apply to 3D images. Yeah.
And just one quick question: do you know the number of parameters does this neural network have?
The number of parameters of this network here? I know. What's that?
I mean, approximated number, not exactly the number.
Yeah, by heart like this, I don't know. It's written somewhere. I can check, but I don't remember out of the top of my head.
Okay.
But it's I think it's like a 10, in the order of 10 million, 6 million, 5 million parameters, something like that. But don't quote me on that. I'm not sure. I don't remember.
Okay.
But I think it's in this ballpark. This is the data set I used to train. So at first we tried, okay, so let's train a model for patella, model for lateral tibia, model for lateral medial tibia. The thing is that I only had like 1,000 patellas, 1,000 tibias, and 1,000 femurs. So it's not very large data set. So we decided to try to combine these different. So and the model was overfitting a lot because we didn't have a lot of data. Even using a lot of data augmentation, I did rotation and translation and flipping and all that, and still it was overfitting a lot. So I tried to improve the number of samples by training different structures together. So I took the advantage of the fact that the tibia, the cartilage of the tibia was something like this. I got the patella and I did like this with the patella. And I fooled the model to think that they were all the same structure. They were not the same structure, but we were hoping in that by doing that the features in the image that belong to the lesions of the cartilage, like markings in the cartilage, they would be similar in shape and the geometry of the features of the lesions would be the same. So we trained both lateral and medial tibia and patella together. So I just get the patella and I flip the patella like this, and I trained together with the tibia. I did the same for trochlea, medial femur and lateral femur, and all the meniscus horns. So I get the meniscus horns, I just flip it, and I make it the lateral and the medial meniscus, the anterior and the posterior meniscus face the same way, so that the features of the lesions would be similar. And the ACL, the ligament, it's a very different structure. We could not combine with anything, so we trained the ACL separately. However, the ACL is a much simpler, much easier problem it's a much easier problem for the ACL, because the ACL, I can look at the MRI and say, oh, there's a lesion on the ACL. So you don't need to be a very experienced specialist to see a lesion in the ACL. It's basically an easier problem. So we didn't have to do much other than image augmentation. Any questions on that?
Well, yes, I have questions from my side, but I'm not sure if you are able to say something about the data. I would like to ask you about the augmentation method that you use, that only are geometrical transformations, right? You didn't try any, I mean, image pixel level, well, not pixel, voxel level transformations like contrast, variance, or something related with the illumination. But
yeah, so
we don't have illumination here.
I didn't try. So I need to plug in my computer just a second. I forgot to get the. Okay, augmentation. I only did data augmentation to reflect the variability within the data set. So the images that we collected, I didn't use contrast because I didn't use to change the contrast was is important in this specific MRI sequence, because they give you the difference in contrast is where it's what gives you the visibility of the structures, especially the cartilage in this case. So messing with the contrast would generate data that was going to be very different from the actual data that we collect, the actual MRI. So I did not use contrast. I did not use rotation on the z-axis. Why? Because the resolution in plane is very good, but the resolution on the z-axis is not as high. So if I rotated too much in the z-axis, I would generate a lot of interpolation on this axis, and I would maybe kill some of the lesions, some of the features, and the lesions are like a millimetric. And given that the resolution on the z-axis was not that high, I avoided doing rotation on this direction because of that. What else? When I did the cropping, before doing the cropping, I would locate the centroid of the bounding box, and I would give you some noise so that I could translate the image before cropping. I did that, and what else? I did not try to use noise like salt pepper noise on the. I did not try that. Don't ask me why. I don't know why I didn't try that. What else? I think that was it. It was basically location and translation, and flipping. No, I didn't do much flipping either. Yeah, I didn't do flipping as well. Yeah, I think that was it.
Thanks. Leo, do you want to ask something?
No, it's okay.
All right. So I used the same. So I trained again. Going back here, I trained normal, abnormal, and then on the abnormal cases, we did how abnormal. It's a severe abnormality or a mild abnormality. And the ACL, we did the first is it's a reconstruction or not. If it's not a reconstruction, is it a severe lesion or not, and then it's a normal or a partial lesion. The ACL was done a little bit differently. And this is the results that we got. Okay, so this is the results for binary classification and for multi-class. We got over 80% accuracy in pretty much all the models for binary. And for multi-class, this is what we have. It's more than 70% accuracy in all the classes except for bone. For bone, bone is a work in progress for bone marrow edema detection. Is a work in progress, and one of the reasons we do not have a very good accuracy for bone is exactly the problem that we were talking about the cropping part. I use the same cropping. Let me go back to. Okay, so the same image, the same cropping box that I used for the patella here, for example, is the same one that I use for bone. So in one model, we classify the bright part. You're not seeing my mouse, right? So one model looks at this bright part, which is the cartilage. The other model for bone, it looks into the dark part here, which is the bone. Since I'm not sometimes the cropping doesn't give us much of the bone, and I think the lesions might not be in the cropping. So we are working on a model, a cropping procedure in especially for bone. So we trained a model for segmenting the bone, and then we cropped the bone, and now we have to train the multi-class models specifically for bone. But this is the results for that we have so far. Other than that, the models do well. You might, oh, Bruno, how do you know that 75% is good or 71% detection of the pollution is good? Because we have data because we know that the radiologist can do more or less like this. So we compare with the radiologist. So as I told you in the beginning, one of the goals of the project was to be able to reduce the difference between the radiologists, to make the radiologists agree more if they use the model. the aid of the model when they are grading the images. And they don't agree 70% of the time. Is that a question?
What's the? Oh, wait, one question. What's the? Do you know the accuracy of the radiologists nowadays?
If I know what?
The accuracy.
The accuracy of the radiologist. Yeah. So I do have this. It's not on this slide. Yeah, we do have. So we've run an experiment doing exactly that. So we gave 50 images to 3 radiologists, and they would grade the images. Okay, independently. And then, okay, let's talk about this later.
I have a question. What
Yeah, go ahead.
What metrics are you using here?
What?
Sorry, what metrics are you using here? DICE, Jacquard, IOU? What are metrics that are using to compute these numbers?
These numbers is simply the class agreement.
The class agreement.
So it's sensitivity.
Some sort of like intersection over union, something like that. Or...
No. So these numbers here are for the classification problem. I do have intersection of a union and DICE score for the segmentations themselves. It's in the paper. I don't think I have these numbers here, but I do have it in the paper. I know for sure that's in the paper. Not only DICE, but intersection of a union as well.
Okay, thank you.
But here in this slide, these numbers are sensitivity and specificity for the classification networks.
But why sensitivity and specificity are more important for you, or for your work, instead of accuracy, for example?
Because that's a very good question. Because lesions are a very sparse data. Let's say let me show the numbers. What I want to here. Let's look at meniscus. For the meniscus, you can see here. Let me. Right. Okay. For the medial anterior horn of the meniscus, I only have 5 lesions. 5 samples were actually severe lesions for these meniscus horn in particular. So it's a very rare event. Some meniscus are more prone to get injured, but some of the meniscus are, the lesion on the meniscus is not well, they are rare. Okay. So if I train a model that says that it's a no lesion, it's gonna be right 95% of the time. So accuracy is not a very good metric. Accuracy itself is not a very good metric. So we need to look at, especially at sensitivity. We would like the model to be more sensitive than specific. And first, because it's a medical application, we would like to say, oh, there is even if we are not sure if there is a problem, let's say there is a problem, and let's run further investigation. In the end, if it's not a problem, then it's okay. But we would like to. We train the models to try to be more sensitive. And the reason we look at sensitivity and specificity rather than just accuracy is basically the fact that I can, if I train a model that says that 90% of the time it says it's a no lesion, 90% of the time it's going to be right. But that's not necessarily a good thing. because the positive events are rare. Not sure if I answered the question.
Mm-hmm. Yeah, I got it.
Yeah, I have a question, but I'm not sure if this question is okay or is probably misunderstanding. You mentioned something here about sensibility and specificity, but the metrics for this are like related to the classification, but here are not included the segmentation metric, right?
Yeah, the segmentation. This is just classification.
Okay, but for classification, you answered to my colleague Leticia about you use dice and also interception over union, right?
I use interception over union for just to assess the quality of the localization.
But this is not included in these metrics.
It's not included here. I don't show the slides in the slides in this presentation, but you can go to the paper. It's going to be there on the paper. Okay. If you're curious, I can pull up the paper now and we can discuss it if you guys are curious.
Mm-hmm. Okay, I got it.
Another question. You're using this method. You're showing the results independently of the no, I mean you use a separate data set, right? It's, for example, or you are processing the segmentation part here, or not?
Yeah. No, the segmentation is just to localize it, do a pre-processing of the images, so I can crop and have images like this. Okay. So once I do the segmentation, I can crop the image like this, and I use these images, crop the images. Those are 3D images as input to the classification networks. Okay.
Yeah.
And these numbers here are the accuracy numbers for the classification. Only.
Yeah, but only the classification. I mean, you are not processing all the pipeline here and showing the results. Only the classification part in a separate data set, right?
I run the whole. Okay. I do have. So first, to answer your question, these are results generated on a holdout set. Yes. So this is a separate data set. So what did I do? I got all the how many images? How many images on the data set? Well, I got all this number of images on the test set. I don't remember exactly the size of the test set now. And I ran over the whole pipeline, and this is the numbers that the pipeline gives me. If I make myself clear.
Mm-hmm.
You know what I mean?
Can you repeat the last part? Sorry.
Yeah. So I got the data sets, and I input it in the whole pipeline, and this is the results that the pipeline each classification model gives me.
Okay, you run all the pipeline and you have the results. Okay.
Yeah.
I got it.
Okay, Bruno. So you have a model that is 80% sensitive in detecting cartilage lesions. So now what? Now what do you do with that? We want the model to be usable, right? We want to do something with the model that we have. So we developed this graphical interface, if you can call it that, to transmit the results of the model to the radiologist, so that the radiologist can use it in a meaningful way in a clinical setting, possibly. So we translated we got the logits from the output of the classification models, and we look at the logits as probabilities, and we assigned the probabilities to this color code. So if it's for every one of the three classes, in case of meniscus, they are associated with the logits in the output of the model, and then we show the color codes based on the logits, based on probabilities, like this. Rather than just giving a table with full of numbers to the radiologists, we give this color coding, which would be more easier for the radiologist to read. So basically, he can look at the patella cartilage here, and it's red, so it's a severe lesion, and the gradient of the red, so it's not a strong red like here on the meniscus. It's a more mild red, so the model is not very sure if it's a lesion. It's like it's sure, it's 55% sure, if we can say that is a severe lesion. Here it's pretty sure it's not. There is no lesion. It's a normal tibia, and here it's somewhat sure that it's a severe lesion in the trochlea, for example. So we give we acquired 50 other images, and we ran our full pipeline on these 50 other images, and the pipeline in the end gives us a PDF with this image for each one of the 50 cases. And then we gave to 3 radiologists. We gave to 3 radiologists, and they would grade the 50 cases without looking at the model outputs. And then 2 weeks later, they would grade the same 50 images with the aid of the model, looking at these pictures here for every case. And then we compare the agreements between them based on that. So here we are looking at the weighted kappa agreement between one attending, which is a very like a 30+ year experience radiologist, and 2 trainees, trainee 1 and trainee 2. So we wanted to look to see that if, with the aid of the model, the trainees would be agreeing more with the experienced radiologist, that the guy is our ground truth, let's say here. And we show that most of the time, the aid of the trainees grading with the aid of the model improves the agreement between the trainees and the attending, and the level of agreement improved in pretty much all improved or remained the same in pretty much all the regions of interest, in all the experiments, all the comparisons. Any questions on this result?
Yes, I have one question. I don't know if you have tried this situation, but I'm wondering how good is the generalization or trial, let's say, input images from different hospitals, from different machines. Just keeping the same semantic, the measurement. I don't know if you have tried.
I'm having a lot of trouble understanding what you're saying. Sorry, that's it's kind of noisy.
Okay, let me just turn off my headset and try with my laptop default microphone. Just a second. Now, if you now listen to me.
Kind of. Try. Yeah. So let's try again.
Okay. I'll do my best. Okay. I don't know if you have tried this case when, for instance, how good is the model in, I mean, calls the generalization when try out input images from different hospitals. Let's say different images from different machines, because you have tried with MRI images from a specific machine type, let's say, but how about from different images from other country, let's say? I mean, just keeping the same semantic, the joint, but I don't know how good is a model for this case.
Right. So if I understand the question is, how good is the model in generalizing if I ran experiments on other images from other machines, other institutions, and is that the question? Hello.
Yeah, he's
Hello?
writing.
He writes the
Oh,
question.
he's writing. Okay.
Yeah, can you read it, Bruno, or I can read it for you?
No,
if you want? I can read
it
it
because
for you.
I'm in presentation mode and.
Yeah. You can continue with the presentation. He asked, I don't know if you have tried this situation, but I'm wondering how good is the generalization when trying out, let's say, input images from different hospitals or MRI machines. I mean, keeping the same semantic, the knee joint.
Yeah, so as long as it's the same sequence, let me show you what I mean by the same sequence. Went too far. Yeah. So all the models were trained on high resolution 3D fast spin echo cube sequences. These parameters can change a little bit from here and there, but slight thickness, the resolution of the image, and the sequence of the MRI, it needs to be the same because the models were trained for this specific protocol. Okay, and as long as it is this kind of sequence of MRI sequence with this specific resolution, then the model should work. Okay. Can be other vendors, can be other machines, but to answer your question, we tried. Yes, we acquired data from two HSS, which I think is New York, and another clinic, orthopedic clinic in Spain called Clínica Centro. This video here is our segmentation model in one of these external data set, externally connected data sets. So this image here was collected from another institution on another machine, and but the same MRI sequence as I mentioned. Okay, I do not have numbers on here in this slide. I do not have numbers on the anomaly detection part. These numbers that I show here in the slides, this is our test set, our holdout set that we use to generate this evaluation. I have these numbers, similar numbers for this data set that I mentioned that were collected in these two clinics outside. The evaluation, they collected and they manually segmented some of these images, so we can compare the segmentations more closely. And this is one of these comparisons, okay, for the segmentation model. For the anomaly detection model, these numbers are not that good. I don't have the numbers here to show you, but sensitivity and specificity for the external data set is not as good as I show here. It's comparable, and it's comparable to the interpersonal variability that we see here in this table. But yeah, I don't have the slide here. But yes, generalizability is something that we still need to work on. We are collecting more data to try to do continuous learning and fine tuning of these models, and possibly deploy them on the clinic. Did I answer the question?
Yes, sure. Yes. I mean, you just mentioned the deployment, and that was more or less the goal of my question, because when you deploy this classifier, maybe you might have those problems when tried out, or when you would like to extend this app for in different hospitals. But yes, that was more or less my my question. Thank you.
Yeah. So there is still work to be done, especially on the anomaly detection part, especially for bone, and to try to improve generability, do run fine tuning and continuous learning of the continuous training of these models, for sure. We are already doing that for the segmentation. I have results on the improvements of the segmentation and the evaluation of the new segmentation models, but it's an ongoing work. I don't have the slides for it yet. I cannot show you guys these results right now, but the improvement of especially the bone segmentation, the bone segmentation and the bone anomaly detection model is something that we are currently working on as well. And we are discussing the deployment of our models. We are discussing the deployment of our models in the UCSF clinics.
One question.
Yeah.
Have you tried semi-supervised learning? Because I think that there are not too much images about your work, right?
Yeah.
So
and
you try
and the image and the training is like a weekly supervised, right? So we give the image and say, okay, there's a lesion in this image, but the model doesn't know where or how they look like or anything. So we just say, here's the image and there's a lesion here, and the model needs to learn. So it's a weekly supervised training. But what's your question?
Yeah, actually was that. It's okay. Oh, nowadays there is another technique, self-supervised learning. So you can create more data set about from your data set.
That might be something interesting to take a look at. I did not run any assessments on semi-supervised and self-supervised. No.
Mm-hmm.
I did not try that. Might be an interesting approach.
Okay. Another thing, I was reading your paper, and you mentioned here that you are using 17 classification networks, right?
That's what we have in this picture here of the whole. Yeah, here.
That's 17, right?
Yeah. So if you count 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 here, but it's okay. Let's see if I remember this. So it's 6 times here because it's 6 different cartilages. So yeah, so you have patella and tibia, femur and trochlea, meniscus, and ACL. So we have yeah. So it's if you sum all these models for the first part, the normal, abnormal, and the severity staging, plus all the region of interest, you're going to have around 17 models. Yes.
So my question is, I don't know if you try only one neural network in order to train all the 17.
I did not try one model for all of them, especially because the size of the input is different. The way, especially for ACL, the way you, I don't know if you noticed, but I don't segment ACL. To segment ACL is a much harder problem, and we didn't have manual segmentation to train an ACL segmenter. The way we do is, I know that the ACL is between the lateral and medial tibia, is below so I use the segmentation of the other structures to find the ACL and crop a bounding box around the ACL. But why am I talking about this? I forgot what I was going to say.
No, it's okay.
Yeah. So your question was why not one model to solve all the problems?
Or fewer neural networks, right? Because because, for example, if I want to make some tests here using your neural network, I have to load 17 models or even 2 model more of segmentation, right? So I have to load here a lot of models, right? It's going to be difficult for inference.
That is true. So our pipe, we have a standalone Python program that has all the models. So it reads the CVS with that points to the image. So the model goes, load the DICOM image, do the pre-processing, run the segmentations, crop everything, and run all the 17 models, and spit out a table with these numbers and a PDF with this picture here with all the assessments. Yes, it takes like a few minutes to process one image. It's a complex system that we built. It's not a simple solution. But to answer your question, so we tried first here in this step. So I do it hierarchically, right? So I do normal, abnormal, and then the assessment of the abnormality. I tried a 3-class, so normal, mild lesion, and severe lesion. The results were not so good. This separating the problem like this gave us a better result. That's why we went with this approach. So this is one reason why I use more models.
Makes sense.
And the other reason is that the fact that when we do the cropping, and that's why I was talking about the cropping of the ACL. When I do the cropping, in the end, all the different structures will have different sizes. So I could not make the volume of the patella be the same size of the volume of the femur without distortion, without changing the image too much. Yeah, so that's one of the reasons as well. And the features of, and I'm thinking about features, the feature of the lesion, right? The feature of the lesion in the femur is different from the femur, the lesion on the meniscus or on bone marrow. So the nature of the geometry of the features is very different depending on each problem. So maybe it's so yeah. So that might be one of the reasons as well we didn't try a model to solve all the problems.
I have a question here from one person that wrote a message. I will read the message to you, or well, This person say in the anomaly detection part, subspace trace algorithms could be used that are responsible for doing background subtraction, separates background and foreground from a video. Yeah, this is the algorithm for background subtraction. Perhaps it can give better results and does not need much data. So basically, his question is trying to compare background subtraction from these methodologies that don't require data with methodologies with data requirements.
But where the background extraction, where would we apply in this case here? You mean for the localization of the structures on the segmentation part?
The question is related to anomaly detection part.
Okay. Okay, I didn't understand the question. Can you repeat the question?
Okay.
Let's see if I can.
Okay.
Trying to locate the. The anomaly detection part to subspace. I'm not familiar with subspace trace.
Okay.
That are responsible for doing background subtraction. Background for the video, perhaps it can give better results. Does not need much data. Yeah, can be. Okay. Take another note on that and take a look at this subspace trace algorithms.
I have also a question. In your presentation, you said that you have different classification levels, but usually do you have in your outputs like multi-label classification? So one 3D object can have 2 or 3 labels in parallel, or just one? Because you have many levels, so I was a bit confusing about that.
Okay, so I'll go back to the presentation. The screen. Okay. Can you repeat the question, Edgar? So are we talking about?
Yes, about here. For example, I see that in the output you have normal, abnormal, the slide. But you have, can you go back to the slide with the classes?
This one, okay.
Yeah. Abnormal, normal, full thickness, partial thickness. These are classes, right? But it looks like classes, these classes look like a bit subjective. So you can have something that is full thickness and normal. So you can have probably a multi-label output. So it's a multi-level classification for one 3D object. You can have probably 3 labels. Is this possible or not?
I want to say no. So if I look at the patella, either it's a normal patella or it has a lesion on that, right? So it cannot have a severe lesion and be a normal patella. It's you know what I mean? So I cannot I can have I do have multi-class, but I don't have multi-label. It can be normal, mild, or severe, and but it has to be one of those 3. It cannot be a combination of the labels.
Okay, I got it.
Well, I'm done with the presentation. If you guys have more questions, I'll be happy to answer them.
No more questions.
But the presentation is, yeah, go ahead.
No, just saying that no more question from here. Thank you.
Okay.
What about deployment? Have you did you think how to do it, or your company is I don't know if you think about that.
Yeah, so we had some discussions in terms of deployment, but we are not doing it yet. I guess it's it's in the queue of all the models that being deployed. They have models being deployed, yeah, I'm waiting in the queue to be deployed. So, but I think GE will want to use the models in their products. So maybe it's one of the reasons that we are not moving forward with the deployments that GE is going to do it. So
GE, you mean General Electric? Or what?
Yes.
Okay.
GE Healthcare. They are the sponsors of this project.
Oh, nice.
Yeah, good to know. Someone else has another question?
That's it, I think.
Where's the chat?
Okay, so I will put share my camera here. Well, if no more questions, well, I would like to say thank you so much to Bruno Nunez because this presentation was really nice for our team, and I hope also, Bruno, you have liked this presentation because it's probably new for us to have invited people, but I don't know for you if you give many conferences like this, virtual conferences. I hope you like it as well, this experience. But for my side at least, I like it a lot. Even the experience that you have is a lot in the medical area and deep learning.
Yeah. Thanks for the invitation, Edgar. It was great to meet you all, guys, and thanks for all the tips and the suggestions. I will look into send me those papers that you mentioned, Edgar.
Okay.
All right.
Okay. Thank you so much. So I will say some claps from my side. I will give you.
Well, when you guys do, yeah, thank you. When you guys do this again, let me know. I would like to join.
Okay. Thank you so much, Bruno. Have a nice day.
Bye, guys.
Thank you.
Bruno.
Take care.
See you.
Ciao, ciao.
Yeah.